When we were solving second order homogeneous difference equations, what we basically did is we guessed that the solution would be like a geometric sequence, and then we got two different answers, so two possible solutions, and then we added them together and we said that's actually the real solution that satisfies both initial conditions. And maybe you're like, well, it feels like we could just add a bunch of different things together. What's so special about this? How do we know that this is the right solution and that there's no other right solution? And that's what I'm going to prove in this video. So what I'm going to do is we're going to say, the way we're going to prove it is we're going to have a look at, okay, let's say there is another solution, and let's call it un, and we don't know what it is. However, we know that t0 is equal to x. That's given in this question. This is all just generalized. Obviously, a, b, c, x, and y are usually numbers. So t0 is equal to x, but if un is also a solution, that means that u0 has to be x as well. And similarly, t1 is equal to y, and if u is a solution as well, then u1 should also be equal to y. Okay, so we know that. So now what I'm going to do is I'm going to say, again, and this might seem arbitrary, but this is just a proof. It's not something that you need to be able to come up with yourself. It's just something interesting that might have arisen from the last videos. I'm going to define a function called dn. And dn is going to be basically just tn minus un. It's going to be, so I'm calling it dn for the difference, okay? And the difference is equal to the tn minus un. And what I'm going to try to prove, I'm going to try to prove that dn is always equal to 0. Or in other words, the difference between these two, the difference between tn and un is always equal to 0. So if I can prove this, well, then that means that tn is equal to un. Okay, so now I'm going to prove it. And I'm going to prove it using induction. So the first thing we do is we prove it for n equals 0. You could prove it for n equals 1, but since we're starting at 0 here, we have to start at 0. So is it true that d0 is equal to 0? Well, it is, because d0 will be equal to t0 minus u0, and t0 is equal to x, and u0 is also equal to x, so that whole thing is equal to 0. So it's true for n equals 0. And then we do the inductive step. So basically what we do is we assume that our proposition is true for some letter k, some number k. So one way you could think about this is saying our proposition is true for 0. So we're going to assume that our proposition is true for k. So that basically means that d of k will be equal to 0, which is equal to tk minus uk. Okay? And the way that induction works, you don't cover this in the leaving cert, but there's a principle called strong induction. So you know how induction, the idea is that, like, if we can prove that p of k implies p of k plus 1, then we can just let k equal 0, and then 0 implies 1, and then 1 implies 2, 2 implies 3. There's a logical, it's the exact same logic if you say that p of k and p of k plus 1 imply p of k plus 2, okay? Because if this is the case, well then if 0 and 1 are true, that means that 2 is true. And if 1 and 2 are true, that means that 3 is true. So it's kind of the exact same logic as normal induction, except we're going to need two starting cases, because to start off this induction, we need to prove that 0 is true and 1 is true, and that will mean that 2 is true. And then 1 and 2 will imply 3, and then we kind of work our way up the ladder. So we actually need to prove this for n equals 1 as well, in order for this strong induction to work. So is it true that d0, is, or d1, sorry, is equal to 0? Well, yes it is, because we know that t1 is the same as u1, because they both have to be the same starting conditions if they're both solutions. So yeah, that's true. Same logic as here. Okay, cool. So now we're going to assume that it's true for k, and I'm also going to assume that it's true for k plus 1. So I'm going to say that dk is equal to, dk plus 1, sorry, is equal to 0, which is tk plus 1 minus uk plus 1. Okay, and now we're going to see if it's true for, we're going to take these two facts to be true, and now we're going to see if we can use those to prove that p of k plus 2 is true. So what would it be for p of k plus 2? Well, for p of k plus 2, it would be that dk plus 2 is equal to, well, we're hoping to prove that it's equal to 0, but we don't know that yet. However, we do know that dn is equal to tn minus un. So we do know that this is equal to t sub k plus 2 minus u sub k plus 2. We do know that. That's a fact. And we need to try to prove that this is equal to 0 using these two assumptions. So tk plus 2, we might want to write that in terms of the two previous terms, because we can do that. All right, let's have a look. Okay, well, we can't do it for uk plus 2, but we can do it for t. Sorry, that's a lie, we actually can. But anyways, we can go through this. So the idea is that basically t sub k plus 2 will be equal to, what will we have? We'll have minus b sub t sub k plus 1 minus c t sub k, all divided by a. So that's just rearranging this equation and replacing n with k, which we're allowed to do. Okay, so since we know that un is a solution, right? So if un is a solution, that means we can sub it into the original equation and it will be true. So that means that it's also true that a times u sub n plus 2 plus b times u sub n plus 1 plus c times u sub n is also equal to 0. This is also true. And that's because u is a solution, so it can be subbed in as all these tn's, okay? So that also means that u sub k plus 2 will be equal to minus b times u sub k plus 1 minus c times u sub k all over a. Because we know that these are both solutions, we can sub them into the original equations, and these equations are true. Okay, and we can use these facts. No assumptions going on here. So d sub k plus 2 will be equal to t sub k plus 2, which is this, minus, and we're going to have u sub k plus 2. So I'm going to actually just change this. We're going to be subtracting this thing. So what we end up doing is we're going to get plus, okay? We're going to get plus b u sub k plus 1 plus c u sub k. And this is all still over a. So I'm going to combine it into one fraction. Okay, so this is where we're at now. And we need to try to prove that this is equal to 0. And we can actually do that because it's quite nice. From up here, from our assumptions that p of k is true and p of k plus 1 is true, this means that uk is equal to tk. And tk plus 1 is equal to uk plus 1. So that means that this, so I can replace tk plus 1 with uk plus 1. So you have minus b times uk plus 1. And I can replace tk with uk. Minus c times uk. Plus b times uk plus 1. Plus c times uk. All divided by a. And as you can see, this term cancels out with this term cancels out with this term, so it's equal to 0. So the difference between the two sequences is equal to 0 here as well. So yeah, that means that the two solutions are exactly the same, because they're equal. If the difference between them is always 0, by induction here, that means that the two solutions have to be the exact same. So even though we were just guessing that this is a solution, it turns out that this is the only solution. So this proves that that is a unique solution.